because you got to do a bunch of research to write those articles. So that's kind of what got me into it, just really wanting to be able to put a name on everything. Well, microscopy is really cool for a couple of reasons. One reason I like it is because it's like a whole other layer of beauty to the mushrooms. So, it's really fun to find them, but you put them under the scope and they look completely different. And some of those microscopic features are amazingly beautiful. Like the anoscobies will have cystidia, like lots of cystidia on the gills, and they'll have calcium oxalate crystals on the tips of the cystidia, which look super awesome. So there's a lot you can see with the microscope that you cannot see normally, but it's mainly for identification. So, for hundreds of years, people have been identifying mushrooms using microscopic features. So if you find a mushroom, sometimes you can tell what it is just by looking at it, and sometimes two different mushrooms will look the same, and that's when you use a microscope. And if you have two very closely related mushrooms that usually you will not be able to tell them apart with a microscope. So the microscope is really good when you have two different mushrooms that are not related, but they happen to look the same due to convergent evolution. But but they have way different microscopic features, so that's when they really help. Usually the gill edge is the first thing I look at, because the gill edge has cells called cheilocystidia, and cheilocystidia are really distinctive. And very often, just after a second or two of looking at the cheilocystidia, I can figure out what genus it is. And then in the gill edge, you also have lots of spores, so you can see all the spore size, spore shape, and spore ornamentation, and whether or not it has a germ pore. And then just a little bit back from the gill edge, you'll see the pleurocystidia. So you can see all those things, but just grabbing a little bit of a gill and throwing it on a slide. I would say the spore morphology often will tell you the genus, and it doesn't tell you a whole lot about the characteristics of the fungus, although a little bit, because often mushrooms that grow in colder areas will have larger spores. They seem to survive better the cold, and then the mushrooms that grow in warmer areas tend to have smaller spores. And then also the spore pigmentation, I think there's a whole lot of pigments that are in spores, and that varies by genus, but I think the pigmentation is supposed to block the ultraviolet light, because the white spored mushrooms get sterilized. The spores get sterilized pretty quickly by the ultraviolet that comes from the sun, which disrupts DNA. So black spored mushrooms are much more likely to be able to travel around the world and be a worldwide thing, whereas white spored mushrooms are much more likely to be localized and endemic to a certain area. There certainly are, and they just, with the advent of DNA sequencing, they started just pulling up, core samples of soil and sequencing all the fungi in there, and they were surprised that maybe 80% of the sequences they got back were sequences that definitely were fungal, but didn't match any mushroom that they had ever seen. So it turns out that most of the fungi in this world never make mushrooms. They never make any fruiting body whatsoever, and you're never able to see them. So a lot of them are just in the soil, and they're super important for the health of the forest and the ecosystem. But they are only mycelium, and they might make little asexual spores on the mycelium itself. So they don't have fruiting bodies. They don't make the normal spores that mushrooms make. But they're definitely super important to the forest. And then many of them are endophytic. So endophytic fungi are inside of trees all the time. And so some of the mushrooms that you see, they can be, just on the forest floor or growing on wood, but then they can also be endophytic. So sometimes they will live inside the tree until the tree dies, and then they have a head start. They're the first thing to be able to make mushrooms and fruit on the tree when the tree goes away. But other fungi are just always inside the tree and never make any sort of fruiting body whatsoever. And so you'll never see them except if you slice it open with a microscope. And there's a stain that's called chlorazol black. And chlorazol black only stains chitin, so using that stain, you can start to see the endophytic fungi pretty well. That's a really good question. There's a bunch of places that you can order it online, and I ordered some, and they messaged me back, and they wanted my doctor's license, and they only sell it to doctors, which I thought was weird. So right now I'm looking for a doctor who wants to buy me some Chlorozol Black. But I can't imagine why they would do this. Yeah, I can't imagine why they would do this, except, maybe people were using it to practice medicine without a license. So this is the stain that they'll use. Like, they'll take a sample from someone's skin and see if they have like a fungal infection, like athlete's foot. So maybe they don't want people to be able to do that. But even that doesn't make sense to me. So I have no idea why they only want to sell it to doctors. But I'm sure I'll get a hold of some pretty soon. Yeah, I'll break it up into. I'll get a bunch of it and break it up into little containers and mail it out to anybody who wants it. And that's what I do now with Melzer's. Melzer's reagent is really hard to get, so I make it and send it out to people. They'll mostly look for the presence of sugars, and so they can like detect the if there's food around. So they'll germinate in sugar water, and a lot of times you can actually put them on a microscope slide and then mount them in dilute sugar solution, and you can watch the spores germinate. And, it takes a while for them to really make a lot of mycelium, but they'll germinate pretty quickly. And just every few minutes you can come back and look through the microscope and see the mycelium has grown further. Yeah, so some of the spores have a germ pore, and that's the germination pore, and that's a little round thing at the end of them. So you'll see that in Staphylococcus, Psilocybe, Hyphiloma, and some of those other Staphylococcus type genera. And then other spores are just like, don't have any germ pore, but they'll find a way to germinate anyway. And then some spores are huge, like truffle spores are 80 micrometers long and spiky and absolutely beautiful. That's for the Oregon white truffle. And then like the smallest spores would be like stinkhorn spores. They're like 2 by 3 micrometers, and they're super small little cylindrical things. Yeah, I think my favorite ones are the segmented spores, and those are on like Trichoglossum, but also on the Pestalodiopsis microspora. And Pestalodiopsis microspora is the one that eats the polyurethane. Yeah, it doesn't really work, but it makes cool spores. Basically, the deal is that it does eat polyurethane, but only in aqueous solution. So it cannot eat a piece of plastic, even not very slowly, but it's kind of like that floor varnish type stuff. That stuff is aqueous polyethylene, or polyurethane, and that it will eat. Yeah, plastic is really difficult for bacteria and fungi to eat. So there's a couple fungi that can eat away at it really slowly, like they'll go to a garbage dump and find culture plastics that's been in there for 50 years, and sometimes bacteria and fungi will evolve to be able to metabolize it very slowly, because plastic has a lot of energy in it. It's a polymer of hydrocarbons, so it has as much energy as gasoline. So if the fungi can unlock that, they can have a very concentrated food source that'll last them a long time. But at the same time, the molecules are in polymers that are bound up very tightly. So they don't have the enzymes that they need to break down those polymers into molecules they can use. At least not most of them, so it's very difficult for them. Yeah, I mean, people love to share that stuff on social media, so all the clickbait sites pick it up and, just get it for all the clicks. But I think bacteria are maybe a little more promising than fungi for eating plastic, because it's easier to engineer them to contain whatever enzymes you want, and they also reproduce faster. But I'm not sure if really composting plastic will ever be the right way to handle it. I think the best way to handle plastic might always be just to melt it down and reuse it. You could melt it down and turn it into a roadway or something. Because composting plastic sounds great, but then you got to mine more oil out of the ground to make new plastic. So why not just use the plastic, all the oil we already mined, and reuse it again? Yeah, absolutely, yeah, for sure.